Hello guys, welcome to Bugs in Code. The problem that I'm going to explain today is BST Maximum Difference. But before that, if you are new here and a person who likes stuff related to coding, then you can subscribe the channel so that you get notified when I push a new video. Okay, so let's get started. Here is the problem statement and it says that you're given a binary search tree and a target value. You must find the maximum difference between the sum of node data from root to target and from target to child leaf node. Okay, and initially you are at root node. Okay, so it says that we have a difference formula. Difference is given by sum of values, sum of actually node values, sum of node values from root to target and minus sum of values from target to leaf. Okay, so this is the formula that we have and we have to maximize this difference. Like I will have some difference and I have to maximize this difference. Okay, it also says that if the target value is not present in the tree, then return -1. And now one example is given here. Let me explain the example. So I'm going to use this tree. Now in this tree you can notice one thing, that the difference is given by the sum of target to root to target and target to leaf, but there are two leaves possible. Okay, so I'm going to explore each option that I have. Okay, so the first of all the target to leaf sum. So the root to target sum is given by 25 plus 20, so it will be 45. This is the first thing that we have. The second thing that I have is we have two options. Like the first is 20 plus 15, which gives me 35, and the second option is 20 plus 22, which gives me 42. Now the difference will be given by, the first one is 45 minus 35. This is the first option. Like 45 is this and 35 is this, and we have 42 here. So the first one is 45 minus 35. Okay, and the second one is 45 minus 42. So 45 minus 42 is the second option. Now the difference here is 3 and the difference here is 10. Here you can see that 10 is the maximum difference that we can achieve. So that's why 10 is going to be the output in this example. Okay, now I hope you guys got the clear understanding of the problem statement. Now let me talk about the solution. Okay, so what I'm going to do is, first of all, I will start with the intuition. Let me write the difference formula again. So difference is given by sum of root to target. This sum denotes the sum of all the node values minus sum from target to leaf. Okay, now in this formula I'm even going to take the same tree as example. So I have this tree. Now in this formula you can notice one thing, and that thing is, this is something which is going to be constant. Like target is at a fixed position. Okay, and root to target sum is always going to be constant. Like it is 25 plus 45. Now something that is variable is this thing. This is variable. Let me write a variable for this. So it is variable. Why I am saying this? Because you can see that for the same target there are multiple leaves possible. You can see that there is one leaf which is 15 and the second leaf which is 22. Okay, so we have two options to consider, and even you can see in the example that we have considered two options. The first one is 35 and 42. Now so we have two options here, and even there are multiple leaves possible. Like if there is 13 and there is 17, so you can see that now there are three leaves possible. Okay, now one observation that I can write is, I can write one observation from this. And what's that observation? It says that in order to maximize this difference, since I can't change this, so I can change this, so I'm going to minimize this term. minimize this term. Like the first observation is minimize minimize root to leaf. Okay, no, actually it's not root to leaf. It will be target to leaf. Minimize target to leave sum. Now, when I minimize this sum, then it is automatically going to be maximized. So in order to maximize this, I have to minimize this term. Now, I hope you guys are able to understand what I'm actually trying to say. We have to go some mathematical here. So it is based on mathematical understanding. Now, I'm going to talk about the approach. I hope you guys are clear with the intuition. Now let me talk about the approach. So let me put this tree here, and now let's talk about the I'm going to divide this question into two parts. Okay, so two parts. The first part says that calculate root to target sum. Okay, sum. And the second part says that minimize and calculate target to leave sum. Okay, and I can also write it like calculate the minimum target to leave sum. Both means the same. Okay, fine. So the minimum target to leave sum in this case is, I have one option as 35 and I have 42. So minimum is going to be 35. And now even you can see that we got our answer when we consider 35 as the second sum. Now I am going to explain each of these part in detail. I will first start with this thing, and then I will talk about this particular thing, the second. Okay, so let me start with the first, which says that calculate the root to target sum. Okay, so let's remove all this. Now, okay, root to target sum. Let me write it as a heading. Root to target sum. Okay, let me take the same tree as example. And in this tree, I'm just going to change the target so that you will be able to understand how to search for a particular value in a binary search tree. Now, if you are someone who knows how to like search for a value in a binary search tree, so you can skip this part and you can okay, so you can skip this part and you can start from the next part, and then you can see the code directly. Okay, fine. I'm going to explain this part for those who don't know how to search a particular value in a binary search tree. Let's take the target is this 45. Okay, so I have to calculate the sum from like root to target. What I can do is I will start from this root. Okay, and then I will check whether my target value, like one property you should know about binary search tree is all the values on the left of BST are something which are smaller than this 25, and all the values are on the right of this binary search tree are greater than this root value. Okay, and this is true for any node. Like if I have this node, then all the value on the left are going to be smaller and all the value are on the right are going to be larger. Okay, similarly for this node as well, it is true for all the nodes. Okay, now I don't think I should write this thing. So okay, let me explain. Let me write the code here. So I'm going to have a function which is going to have root and target, because I have to search for this target. Now one thing is sure, that if my root is null, then I can simply return the target is not found. So not found, isn't it? After that, if my root is equal to target, then I can simply return found. Okay, fine. Now what else I can do? One thing you know about binary search tree that I have already told you, all the values on the left are smaller. So if the target is smaller than root value, Okay, in this case, now you know that the target value is something which is less than root value, so you will simply move to left. So I will search, like I will return function. This function is actually find function, and function left, like move to left, move to left. Okay, so it is going to search by moving on to left. And the second option is else. We have, okay, so if it is like smaller and it is not equal to root, then it is going to be greater than root. So in that case I am going to return function for move to right. Okay, you can see that this condition is false, because if we have reached this condition, then obviously these two are going to be false. So this means root is neither equal to the target is neither equal to the root value, nor it is smaller than the root value. So in that case it is obviously going to be greater than the root value. So that's why I am going to write. This is the function for searching. But along with this search, one interesting thing is, along with this search, I have to return the like sum as well, like root to target sum. So how to calculate this? In order to calculate the root to target sum, what I will do is, I will make, first of all I'll make this function like int. It is going to return an integer, and find, this is going to have root and it is going to have target. Now what I will do is, first of all I will write the same condition, like if root is null, then it is not found. Okay, so how to represent not found? I'll simply represent not found by return min value. Min value. Quite simple, right? After that, if my like root is target, root is equal to target, then return target value, or I can say root value. Why I am saying this? This is very important, because I have to calculate the root to target sum as well. Root to target sum. So I will keep adding the root values when I have found like my target. So now I will write the same condition. If like target is smaller than root, then I will return, I will search for like left. So find like move to left. But interestingly, suppose that I have found the value on the left, so in this value I have to add my root value as well, so that I can keep track of this sum. Okay, I will even explain the dry run of this approach. First of all, just see here. So else I am going to move to right, return root value plus find move to right. Okay, now you can see one thing, that okay, here suppose that I have found the value here, like here I have the value 45. So it is going to give me the sum recursive, like 45 plus 35, and when I have this sum, then I have to add my root sum in that sum as well. So that's what I am doing here. Like you can see that in the target value I am adding the root value plus find. Now this is the pseudocode for the first function, like the first task that we have. The first task was to find the root to target sum, and this is what I am doing here. Okay, now let's talk about the second thing, and the second thing was minimize and calculate the like okay, target to leave sum. So let me write this. Calculate the minimum target, okay, it is target to leave sum. Fine. Now let me take the same tree. So this is the same tree again, and for this tree I am at this position, like I am at this. Okay, one more thing that I want to tell you. When I find the target to leave sum as I have shown here, so along with this I also have to find the target, like because and for this I'm going to start like the traversal from this target, since I have to calculate the target to leave sum. So how to find this target? Here one more thing that we have is I can have a target node. Target node initially is equal, it is equal to null. This is the initial position, and final position for this is going to be target node, which is it will store. Fine. So here when I find the target, then I don't just have to return only, but I have to do one more thing. So let me erase this first. So first of all I will do something like okay, let me highlight this. I will do something like target node. In this case, if my root is target, then target node is going to be root, and then I am going to return root value. Are you understanding what I am doing here? I am simply doing it because since in this function I am only playing with the like integer, but I also have to find this target node value. So you can see that in tree, like in this tree I have to find this 45 as well. Target was 45, so I have to find this 45 as well. So this is what I will store in a variable which is target node. Now that I have the target node, so I can simply start the traversal from the target node. Fine. This is the target node, and I am going to, okay, actually let me take here target equals to 20, because for the previous one I have taken target as 45, but now it is 20. Okay, fine. So I will start from this target and I will find the minimum root to leave sum. Okay, so what I will do is I will have a function which will be having root only. Okay, fine. Now if my root is null, then what to do? Very important. Why very important? Because if my root is equal to null, then what value I will return? It will be of int type. Why int type? Because I have to find the sum, so I am going to use return int type in order to find the sum. Okay, fine. In that case I will return max value. The question is why this max value? This max value because I have to find the minimum. I have to find the minimum sum. So in order to minimize, I will return the max value. Okay, fine. Again, after that, I will return. Okay, so okay. Even the question is, since I have to minimize. Okay, let's see. I will. I may change this value later when I will see an improvement that can be done. From this 20, I can move to this 15, and from this 15, I can move to this null. So in this case, in order to retain this sum, I think I have to return 0. Okay, fine. So instead of this like max value, let me return 0 here. Return 0. Okay, fine. So I'm going to have sum each time, and if my root is leaf, then what I can do? Then I can simply okay, so in that case I can return root value. Okay, fine. And now I am going to calculate for left and right. Since I am at this node, so I will have some left value and right value. So I am going to calculate, like I have left as function for root dot left. Okay, and I will have right value as function of root to right. Now I have the answer for this value and this value. So what I can do is, whichever gives me minimum, like either left or right is going to give me minimum, so I will find which is giving me minimum. So let me erase this function is going to extend. So I will find the minimum as minimum of left and right. Fine. Now I have the minimum of left and right, and in that minimum I am simply going to add the root value because I have to find the sum. So I am going to add root value to this. This is something that I have to return. I am going to return this value. Now this is the second function that I have. So I have explained both functions to you. Okay, and even I think this is something which is really suspicious. Let me talk about this. If my root is null, in which case root can be null? This is my question. Like if I have this tree, then I will start from this, then my root is not going to be null. So I don't think there will be any case in which a root can be null, because I'm already returning when I have leaf. Like if I have leaf here, then I am returning the value. Similarly for this, only case where root can be null is when I have not found the target. Target not found. Target not found. So why not to return -1 in this case? This is, I think, better. Okay, fine. Now I have explained you both the functions, and I hope you guys are clear with the problem and the approach. Now let me talk about the code. Okay, so here I have the code, and you can see that on the left side I have Java code, and on the right side I have C++ code. Okay, fine. So I will start from this position. I have taken the target node. This is the reference variable which stores the target node if it is found. Okay, and you can see that I have already explained you why I am taking this target node. Okay, fine. Now this function find is going to give me like root to target sum. Okay, fine. And you can even see that the C++ code is here. So first of all, I am taking a reference variable which is null, and after pointer is used to like do something like call by reference in C++, and in Java we do it with array. Okay, fine. So now here as well you can see that I am first calling root to target. Okay, function. So now I have this function as my root to target function. You can see that the same thing I am doing here. Like if my target value is greater, then I will move to right, because target value is greater. Okay, fine. If it is smaller, then I will move to left. And I have the target node, so whenever I find the target, then I will first store it in target node. Okay, and after I will return the target. And even you can return the same value, both means the same. Like I can return root value here. Okay, I mean root dot data for the code. Okay, and the same code is used for C++ as well, you can see here. Now let's talk about target to leaf sum. This function is going to give me minimum target to leaf sum. This is very important. So now let's talk about this function. I have this function. So if my root is null, root is going to be null when I have like, okay, in which case root is going to be null? Obviously when target is not found, so I'm going to write -1 here. It doesn't matter which value I write. Okay, so I can even write -1 here as well. Fine. Now I can do the same thing like if my root is leaf, so this is basically condition for checking the leaf, and I can simply return root data. And now I can calculate the like for left and right value, and then I'm simply going to minimize it. I'm not adding the root value because I have already added this root value. So instead of doing this, I can also do one more thing, that is like I can do this. Both means the same. Okay, fine. So this is the code that I have, and I hope you guys got the clear understanding of the problem. And you can see one more thing, that I'm also checking one thing. If my target is not found, then I have to return -1. This is what the problem said to me. Okay, fine. Now this is all about the problem and the solution. I hope you guys like the problem and solution the way I explained. So thank you.